Good morning. I'm glad to see you all made it here this morning in the rain. My name is Edward Wright. I'm a senior researcher with the Space Studies Institute and the chairman for this event. It's certainly good to see you all here and back here for our first conference in 11 years. As you may know, this year is a very special year for us. It's the 50th anniversary of Apollo 11, of course. Everyone has been celebrating that. But it's also the 50th anniversary of Gerard O'Neill's High Frontier vision. Back in 1969, as men were landing on the moon, Gerard O'Neill was teaching a freshman physics seminar at Princeton University, and he asked his class one question: is the surface of a planet the best place for a high technology advanced civilization? And somewhat to his surprise and the surprise of the students, the answer came back, no. Professor O'Neill determined that it was possible to build these very large space habitats containing thousands and eventually millions of people, and that with the extraterrestrial resources available on the moon and other bodies, we could build more of these living habitats and provide far more space for human beings than we have available on any planet in the solar system. Of course, there was also the NASA Ames study in 1975, 76, I'm not sure the exact year, which updated that and produced the Stanford Torus. But there's been very little work done on updating the O'Neill vision since then. There are some individual researchers who have some ideas, but the Space Studies Institute has not really gone back and taken a look at the vision in the preceding 45 years. So right now, what we're doing is starting a new project called the Space Settlement Enterprise. We're going to go back, we're going to look at the O'Neill vision from top to bottom and find out what needs to be updated. You know, as much as we all love O'Neill and the High Frontier, the fact is a lot has changed in the last half century. We have new knowledge from the solar system, we have discovery of water on the moon, we have photographs of asteroids that you know, no one thought we could see 50 years ago. We have new space companies such as SpaceX and Blue Origin emerging. We have new technologies that have been developed in that time. So we need to find out how all of these things play in with the High Frontier vision and bring it up to date and come up with a High Frontier 2.0 for the 21st century. And this conference is the first step in that project. Our mission here this week is not to find all of the answers, it's to find the questions, to determine what we need to do, what we need to update, what the missing pieces are, the new technologies that need to be developed. We need to come up with a roadmap for the next few years during which we're going to be working to update this vision. And so I'm glad that you're all here to help us with this venture. If you're one of our speakers, we're looking forward to hearing your ideas. If you're in the audience, we're looking forward to hearing your ideas and your questions as well. I hope there's going to be a lot of audience interaction. We've got a couple of microphones that we can hand around to speakers, to audience members so that you can interact. And we'll have frequent breaks in our talks so that you'll have plenty of time to answer questions. I mean, this is not a talking head scenario. We want lots of feedback from everyone here in the audience. And on that note, I'd just like to turn the session over to our first chairman, Mr. Dallas Bienhoff, who's going to be talking to us about habitat design.
Thanks, Ed. Actually, I'm not going to be talking as much as listening like the rest of you because I've got a panel of 7 that are going to talk to us about space habitats from the past to the future. So first, let me set up the screen. So the question is, what do we want to build and how are we going to build it and what are the problems in building it? So that our panelists are going to talk about their ideas, but also the challenges that allow them to get us there. So we have 7 panelists, and if they would make their way up to the stage as I do some introductions, that would be great. Just pick any seat, everybody, all 7. So while they're doing that, I'll give you a little bit of background about myself. I'm founder and space architect for Cislunar Space Development Company. I retired from Boeing a couple of years ago and founded this company to focus on transportation between Earth orbit and the moon and making that a commercial activity using propellant depots and water from the moon when it becomes available from suppliers that would be a different party. But this is not about that. This is about the habitats and what people will live in while they're there. Cancel that. So on the panel, I'm going to do this alphabetically, and then we'll have speakers talk in order of their timeline and size of their facilities. So Susie Bianco, she's a graduate, a space architect of the Sisakawa International Space Center, or Center for Space Architecture at the University of Houston in Houston. It's a great school. They supported a study I had at one time. She recently completed her master's on a 400-person space facility, and she'll talk about that and explain that for us. Talk to us how that works. She's also the co-owner of Space Cooperative and a co-founder of Space Decentral. John Blincow. John is part of the CEO of the Gateway Foundation, former 747 pilot, right? Yep. And if you look at his website, the Gateway Foundation website, this is a large von Braun type space station facility for 400 people and also a larger gateway for space commerce in the cislunar space. So very interesting talk coming up from him. Al Globus. Al is part of National Space Society. He worked at NASA Ames on a lot of different projects, but really he's been sponsoring and co-founded a space settlement design activity for high school and elementary or middle school students, and has done that all around the world. So kudos to Al, and he will talk to us about a space facility in low Earth orbit, which will make it easier to build and less expensive to do that. Anthony Longman. Anthony is part of Skyframe Research, and they have a space city concept. I would liken it to the Bernal sphere, except that it grows. It can grow naturally or what's the other great?
Organically.
Dynamically would be a good word, while you're living in it. So it can expand while people are on it and become a larger facility. We have Bruce Pittman. Bruce is Director of Commercial Space Development at Offworld. He works at the NASA Space Portal, where he's been for a lot of years. I'll let it go with that. He's also a subject matter expert for systems engineering. So Bruce will talk to us about SpaceHab. And Bob Richards, recently retired from Northrop Grumman, recently as in 2 weeks ago. So he's going to talk to us about Gateway, the NASA Gateway, not the Gateway Foundation Gateway. So we have 2 gateways on the stage. It'll be interesting to hear his perspective on the issues of getting a gateway in place in the near rectilinear halo orbit and what the challenges are with that. And finally, Fred Scharmen. Fred is a professor at Morgan State University. He teaches urban planning and design. He also has a new book out called Space Settlements, which is a recap of the 70 studies, the NASA Ames studies, and he'll show us some astounding pictures from that and explain their history and talk about what that means for our future. Let's give him a hand.
Coming for you.
So, like I said, we're going to look at the past and the future of space settlements and how people have lived in space. So we had a long era of capsules where we sent 2, 3, 1 people in space. They spent anywhere from a day to, or part of a day to 2 weeks in orbit, in things from the Soyuz and Vostok and Mercury all the way out to Apollo, and then we have the 2 commercial vehicles coming up line from SpaceX and from Boeing for access to station. And of course the shuttle, it was probably the biggest capsule out there. We had 10 people in that at one time on one mission. Then that was followed by single module space stations. We had Skylab, Mir, not Mir, but I think that's Almaz up there. Spacehab, which is an addition to the shuttle to extend its volume and workspace for long durations in space. Space Lab is up there as well, which is a NASA module that had space experiments in the shuttle payload bay. And now we're in the era of large integrated multi-module space stations that are still somewhat limited in volume and power. 100 kilowatts sounds like a lot, but I think we need a lot more than that. We also have commercial space stations coming up. Bigelow has restarted his process of getting his commercial up there. NASA is looking for commercial LEO free flyers as well for space station. We have the Chinese. We also have the Gateway coming up. And so we'll be moving in that era of newer systems. And then, will the future look like this? Will it be Bernal spheres? Will it be O'Neill cylinders? Will it be Stanford Torus? Will it be the Gateway, Foundation's Gateway? Or will it be something else entirely? We really don't know. It could even be hollowed out asteroids going back to islands in space from Wolseley. So with that, those are my opening remarks, and I'd like to invite our first speaker, Bruce Pittman, up to talk about Spacehab, and we need to talk about the challenges. What are the challenges of making this happen? Bruce? The files are numbered. That should be you right there. There you go. You can get it up to full screen.
Great. Thanks, Dallas. So, well, it's a great pleasure to be here. Always a little about being the old guy that's talking about the past. But anyway, I guess it goes with the territory. It's one of the problems with being around for a long time. So I was part of the startup team from Spacehab back. I joined back in '85. So we're going to take a little walk down memory lane here.
Arrows right there.
So when you talk about Spacehab, this is what most people think about. It's a mid-deck augmentation module here. This was the mid-deck of the space shuttle. And if you looked at it on TV, when the space shuttle was flying, it looked kind of big because they were using a fisheye lens. But if you were ever in there, you could reach out and touch both walls. And so when you put 7 people down there, it was cozy. It was cozy. And let me make the usual caveat that, although I work at NASA, I'm here on my own dime, and these are my own thoughts. So I'm not speaking for NASA. So let me get that caveat out of the way. And this was kind of part of the team here. So over on the right-hand side there, the guy with the big grin is Bob Citron. And he was kind of the guy that started this whole thing. He's the guy with the tan, But next to him, over on the right-hand side of the screen there, is a guy named Tom Taylor. And it was really the marriage of those two guys, the coming together of the cooperative, if I can use the word genius, of those two guys. Because Bob was a marketeer per excellence. I mean, he could sell, water to fish. He was really good, but he wasn't an engineer. Now, Tom was an engineer, but he wasn't an aerospace engineer. He was a civil engineer. And so he had built a metro system in Washington, D.C. He did the habitation modules for the North Slope of Alaska, for the Alaska pipeline construction. So he had all of those lessons learned that he learned from that. And then over on the guy with the mustache there, that's me back in my earlier days. Over here on the left-hand side is some of the team, and the short guy in the middle there is John Spencer, and I'm going to come back and talk to him for a minute. But what I wanted to do is take, as part of this trip down memory lane, just to go show you that Space Hab module, this is not what Bob set out to do. What Bob set out to do is he wanted to put a passenger module and carry up people in the shuttle cargo bay. And NASA's comment was, what part of hell do you not understand? Hell no, do you not understand? And, but Bob was persistent, and he kept trying to sell this. So what happened was when he met up with Tom, Tom convinced him to ask a better question. And that was, well, if you don't want passengers in the cargo bay, what do you want? And this comes back to, if you go, those things on the wall in the mid-deck there are appropriately called mid-deck lockers. And this is where the astronauts stored their food and their clothes and their, experiments and stuff like that they were going to do on a mission. And on each flight, there was usually one or two of those things that were empty. And so NASA started giving out an AO, an announcement of opportunity for people that wanted to put experiments in those lockers. And that really caught on. People went crazy. So NASA started signing up people for these things, and they signed dozens and then hundreds of these agreements that they had no way of fulfilling. See, this is called a market. This is called a market opportunity there. So where this whole thing came around, what NASA said, well, we could use a little extra space. We don't want to fly private citizens in the shuttle cargo bay because there's a number of safety reasons why you just do not want to do that. They were absolutely right in that call. But they said we could just use a spare room up there. So when I joined Space Hab in 85, we were looking at how could we do this simply and cheaply. And what we had originally hoped to be able to do was what was called a passive module. You would basically have a module up there, but you didn't hook into the cooling loops, you didn't have power and all that. But when we went out and started doing our customer surveys, we found out that that's not what they wanted. And it's one of those things like Pandora's box. Once you start petting in power and you start putting in people and all that, then pretty soon you're off to the races. And so what it ended up where we were hoping that this thing would originally cost about $50 million to do this, it ultimately ended up about $150 million to actually build the module. But through a series of serendipitous kinds of things, one of the things I wanted to highlight was trying to get people to take you seriously. So going back to my picture of John Spencer again. So John's the guy in the middle there. He's an architect, by the way, and he did a lot of work on space theme parks and all kinds of stuff. So remember, this is back in the mid-'80s. Anybody remember a movie called Space Camp? Kind of a campy movie, if you'll pardon the pun there. Well, what they did is they built a full-size mock-up. This company down in Southern California built a full-size mock-up of the space shuttle. And it looked pretty darn good. So what we did is we had them build a mock-up of the Space Hab module of what we thought it was going to look like. And then I talked to one of my old bosses when I was a civil servant at NASA. I talked to one of my old bosses there into letting us put the module in the building I used to work in. So we had this empty space that we did, and so we put it there. And then we hired a couple of astronauts, Byron Lichtenberg and Owen Garrett came in, and they were retired astronauts, and they came in, and we took video of them. And then we went to the IAF in Austria, in Innsbruck, and we had a booth, and we had demonstrations, and we showed this video, and it looked real. I mean, so people started taking us seriously that, hey, maybe there's something there. And I started giving seminars on user experience and user accommodations and handing out questionnaires. And one of the things that we were able to do is get letters of intent. You know, if you have this vehicle available, if you have this thing at this price point on this time frame, we would be interested in using it. And we got some big name companies to do that. And that kind of gave us the original impetus that finally got some traction with NASA. And ultimately in 1990, they were able to get the deal that they worked with NASA was an interesting one, is that it really was the first partnership, and that basically SpaceHab was going to develop this vehicle that would go in the cargo bay, and NASA agreed to that. But since they were using a government asset, which was the space shuttle, we actually had to pay them to put the module in the shuttle cargo bay, and then they wanted to use the mid-deck locker. So in 1990, they signed up to buy 2/3 of the modules, 200 of the 300 modules on the mid-deck lockers on the first 6 flights of the SpaceHab module for $186 million. So it was this weird thing, I pay you, you pay me, you know, this is kind of an offset kind of a deal. But ultimately, in 1993, the first SpaceHab module flew. In various versions and configurations, it flew over a dozen times. I think it was 15, 17 flights of that. And unfortunately, in the Columbia accident, they lost their double module. And then they did something really stupid. They sued their customer. So SpaceHab sued NASA. Which was not a really good thing to do. And so it was an interesting learning experience. I think there's a lot of good lessons learned there. I'm a big fan of the idea of strategic pivots. If you're going down one road and it ain't working, it's good to go take a look at other things. And this is kind of what a cutaway view of, you can see how it looked like. The flat end caps were really important because on Spacelab, you remember they were conical, and this was flat. Which was really important because the way that NASA came up with the pricing for the SpaceHab module in the space shuttle was by the feet of the cargo bay that it consumed. So by having flat end caps, we used much less of the cargo bay than we would have if we had the conical end caps. And then this is what it looked like on orbit. There's a picture of it on the ground with them loading in the thing on the back wall there is the mid-deck lockers. And this is what it looked like up in space. And it was really an amazing thing to see that thing actually up in orbit, you know, something that you had worked on. Now, I was only involved in the first couple of years when we hired Jake Jacobson. This is another cautionary tale for entrepreneurs. We hired Jake Jacobson, who is from McDonnell Douglas. He brought in his team to actually do the development, and then all of us entrepreneurs were kind of invited to leave, except for Bob and Tom. So that's one of those other things. You got to be ready to be replaced. So it was kind of successful. They did a public offering on the NASDAQ. It did really well. I actually made some money on this one. When I sold my stock, I actually made some money, which is a good thing in the space business if you can make some money out of it. But there are a lot of lessons learned. And this really was a learning experience. There was a lot of good things that came out of this. And this actually helped influence the COTS program that we did back in the mid 2000s and 2006 with SpaceHab and Orbital, but that's a talk for another day. So on that note, I will interested in your questions.
Thanks, Bruce.
Yeah.
Just for the moment, what was the biggest challenge, other than money?
You know, it was basically the safety stuff, I think, was one of the big things, is just trying to get everybody to be comfortable with you know, that the vehicle was going to be safe and all that stuff. So it's like I said, it's kind of a slippery slope once you start getting into that stuff. It's actually a very sharp, very, you know, steep learning curve. Right. And so this is where McDonnell Douglas really came in and did provide a lot of expertise in that area that really helped a lot.
Okay, thanks. So from SpaceHab, you know, we went through and built a space station. We don't have a speaker here from the space station. I was part of the Russian integration team for about a year with NASA. I was a co-chair of the co-lead with Doug Drury on the for the FGB, the first element of the space station, the functional cargo block from Russia, worked with Russia for getting the requirements for that set, and left that program about a year before it was supposed to launch. But the biggest challenge on space station was the integration, making sure that the vehicle could fly as each new module was added to it, because all of the subsystems were integrated together. They were not independent. The modules are not independent. They work together on the US side, they work together on the Russian side, but they had to fly together, and walking through that assembly process and making sure that the vehicle would fly, but also planning out the EVAs, because all of the external connections, I think, is what drove some of the issues with space station, and getting the modules connected together on the outside with EVA time. So that's a brief transition from the past into the coming future, but on the same scale with Bob Richards and the NASA Gateway project, and Bob's going to talk to us about issues related to that and show us some slides. Bob?
All right. Thank you all for allowing me to speak today. I'm not, well, why don't you? Just turn it off for now. Yeah, I can take care of it. Okay. Thank you all for letting me speak today. I'm not what I would call a regular contributor to SSI, but have been a long-time member. I think I joined in either high school or early college, and actually had the pleasure of working for Jerry O'Neill for just a very short period of time in one of his startups called GeoStar. It's very interesting, and also attended a lot of the Princeton conferences in the kind of early 80s to mid 80s. Since then, my career has hit lots of different parts of aerospace, the space shuttle, but really had the privilege and pleasure to be involved in a commercial space venture, and I say commercial in quotes because I think what constitutes commercial space is sort of slowly changing over time. A lot of it is sort of resonated with what Bruce was going through on SpaceHab. I joined Orbital. I was then Orbital Sciences Corporation really early in its history. It was started by just three guys out of Harvard Business School, and just a really quick story on that. So they wrote a thesis on a business case for space, and it involved, well, there's a space shuttle out there, but there's no way to get to the geostationary orbit, so they wanted to create an upper stage that was optimized to fly in the space shuttle and then take satellites up to geostationary orbit. They wrote a business plan on it as part of their Harvard Business School work, and it received an award. And they were at a black tie dinner receiving that award, and Fred Alcorn, who's Alcorn Oil and Gas, was sitting at their table, and he was so interested and enthused by their talk and their thinking that he whipped out his checkbook and wrote their first startup check for what became Orbital. When I joined, it was probably 50 people or something, but there was not a single CAD system in the company. There was no way to build electronics. It was really just you could write contracts and you could have outside people do the work, but this was the first time of building an engineering team. So I've seen companies being built from small to medium to large, and ultimately Orbital merged with ATK to make Orbital ATK, and then was purchased by Northrop Grumman for, I guess the number was public number, like $9 billion. So Dave Thompson and his startup group really created a lot of value, in space. It was pretty much a pure space play. So in the last 10 years there, I focused on human space flight, and that involved conceiving and bringing the Cygnus product online, as well as for the last few years was involved in Gateway. Gateway was a study funded by NASA. Northrop also put internal funding into it, and we and other contractors really looked at Gateway in terms of design, but also in terms of prototyping some of the riskier items and getting them working on the ground. Now, I left Northrop, retired from Northrop just recently, so today's talk is strictly my thoughts, not Northrop. And so I was trying to think of what's the best way to give you an appreciation of the sort of level of technology that the early parts of the Gateway are going to have. And it's public knowledge that Northrop always pushed the idea of taking the Cygnus and turning it into kind of a poor man's habitat. And I think that sort of size is similar to the Salute station that was up before and represents sort of a minimum size station that you're going to see in cislunar space, some derivative or something similar in size. So I thought I'd play this video and kind of give you a little bit of a voiceover. This is from YouTube, so you can all, if you're so excited about this video, you too can watch it again at home. But I think it has a good sense of technology scale of what cargo resupply to the International Space Station is all about, and then extrapolating that same level of technology out to cislunar space.
You want to full screen that, Bob? Yeah. There we go.
So again, I'm just using this as kind of a representative of design that's fairly recent in this level of technology is what's going to put us in cislunar space. This is the Cygnus vehicle, and it was launched out of Wallops. This is an actual mission. And the Cygnus flies autonomously to the International Space Station and then is grappled by the astronauts and becomes part of the International Space Station during the cargo transfer. So it's a human-rated structure, and you're going to see that in cislunar space as well, where modules of about that size are going to get accumulated. After putting so much delta V into getting it out there, you're not going to want to throw it away. You're going to want to repurpose it if it's a cargo system, or it's going to be outfitted as a habitat from day one, and it's going to stack together. And it's going to have a lot of the same challenges as the International Space Station, where you basically put a lot of small modules together, and so integration is definitely a tough challenge. So this is Northrop's view of about a year and a half ago, but it's pretty close to where NASA is today, although it's going to show the Gateway as both Phase 1 and Phase 2. With the increased emphasis on getting to the lunar surface, they're kind of starting with a minimalist gateway and then moving to a full gateway. So this habitat module would be sort of considered part of Phase 2, and what you saw up there before was the minimalist type of habitat to support a lunar lander, which would be Phase 1. This is also very SLS centric. I think NASA in general is moving towards using more commercial launch vehicles to take modules out to cislunar space. So in this case, the Orion is the tug, if you will, to take a module out to cislunar space, but that functionality could be another tug type of system, which would make it totally unmanned. In any case, you're going to see these modules kind of stack up. You're going to have side ports, like you see there, for the lunar landers to attach. And, it's going to grow over time. It's mostly going to be not occupied, with the missions that are being set up. Typically, it's going to be kind of 2 to 4 weeks on the Gateway. We always thought that one of the first things they do from Gateway is kind of joystick some rovers around the South Pole. That still may happen, but with the increased push towards lunar landers, NASA's actually on a track to have a lunar lander something like this in the video out there in 2024. and 4 people would come out on Orion, 2 would stay in the gateway, 2 would go down to the surface on the lunar lander, have a short stay of a few days, then go back to the gateway, and then all 4 would go home. So, this sort of vision of a couple years ago, it seems like NASA's embraced this fairly closely. We'll see how that goes. And of course, Gateway can be used not only as a stepping stone to the lunar surface, but could be used beyond going to Mars and other things like that. So again, I just kind of use this video as a little bit of tool to highlight a couple of different areas there. And when we get into the question and answer period, I can give you my personal thoughts on various aspects of these different modules and stuff. But the top level functionality is it's a foothold in space. It's in an orbit around the moon. The orbit's relatively easy to get to from an energy perspective, and it's going to be a transportation node where lunar landers can go to the surface. So with that, I'll stop this and thank you.
Thanks, Bob. The key or the proof that this is going forward is, as Bob described, is NASA has several BAAs or opportunities out there for bid. One is to study the lander and look at the transfer vehicle that would move it from the gateway down to low lunar orbit, as well as refuelers to get propellant out to the lander or the ascent stage for the next mission in the transfer vehicle. They also have an opportunity out for the cargo for logistics resupply for Gateway, and that's a commercial opportunity. Its value for an unspecified period of time or missions is $7 billion to one or more contractors. Then there's an opportunity coming up in the very near future. It's called Appendix H, and that is to look at an integrated lander system that would get focus on the descent stage, the ascent stage, and the transfer vehicle as a single unit or as 3 different units to get back and forth in the gateway. So, and these are all commercial-like or public partnership-like, COTS-like activities with the companies that are bidding having to put in up to 10% of the proposed value of their work. So we're going down that commercial path and hopefully laying a foundation for future commercial activities in cislunar space. So thanks again, Bob. So our next speaker is Fred. Okay. Fred is going to talk about planning, urban planning and development, and what that means, and also show us some of the great pictures from the space settlement studies. But this is kind of a prelude into the larger stuff that we all envision and hope to see in space. Fred? I'll get your slide open.
Screen. Okay, terrific. Thanks, Dallas, for the invitation. So my field is architecture and urban design, and for about the past 7 years, I've been researching and writing about Gerard O'Neill's, especially 1975 work on space settlement. And in this work, I'm paying particular attention to this collection of 13 paintings made by 2 painters, Don Davis and Rick Goodis. And they had this really interesting set of backgrounds. Don Davis sort of got his start illustrating planetary science for Carl Sagan's journal. And Rick Goodis was trained as both an architect and as a commercial graphic artist. He also went on to do things like the covers for a lot of the classic Atari games for the 1980s, so you can recognize his style there as well. So these are the renderings that a lot of us are familiar with, and thanks again to Al Globus, my co-panelist here, for putting these up on the web so early on and maintaining that website, because they've really had a kind of lasting influence on culture. And what I wanted to sort of focus on in my book, Space Settlements, was the idea that these renderings were not just illustrations of a technical design project, that they are works of art and design in and of themselves, and that the people who made them, Don and Rick, were really conscious that they were sort of working within larger culture in general. They were integrating sort of cultural influences, and they've had lasting influence since then. And I was really lucky during the course of the research for my book to be able to go out and visit both Don Davis and Rick Goodis in their studios. In Rick's case, I also got to go to NASA Ames with him and see the current home of several of his paintings on site and interview him there. We also got to integrate a lot of their early work in their sketchbooks as part of the project too, so that's in the book as well. And what was really most interesting to me as I was doing this research and talking to the two painters is the degree to which they were making conscious choices about how to portray these spaces. And that really looks good on the big screen, right? It's really terrific to see it in such high res here. This is one of the first paintings produced for the 1975 project, and Rick Goodis remembers this was made under the direct direction of Gerard O'Neill himself, who asked him, make it look like a French landscape. So Rick, with his background in illustration, rendering for architecture, and in sales, he's consciously deciding here, he was talking about this, he's consciously deciding that it probably really wouldn't look like this. He's familiar with cost per square foot, as an architect, and he's aware that space is going to be at a premium. But B, he's choosing to really sell the space, to really make this image into an illustration, but also kind of a marketing and persuasion device here. And then this is maybe Don's most famous painting, also of the interior of the O'Neill cylinder. Don here remembers that he's consciously trying to critique the idea that humans could reproduce a natural ecology in an artificial environment here. So several of the choices he's making about, we can see a city in the distance there, but we're not in the city, we're in the landscape. Are made to really provoke discussion and debate about the possibility that humans could make something like this. And here also Don found a note in his archives from a conversation with Gerard O'Neill in an early phase while he was still making sketches for this painting, asking him to add more and more, quote, cabins, boats, dome buildings, and things that are sort of in between architecture and vehicles. And I think it's really great that Don, the little cabin you can see there on the left, is basically a ringer for the lunar lander. In an earlier sketch, it's just a much more normative little house, and Don changed it up. And then also it's great to find artifacts like this. This is a drawing that was mailed to Don Davis from Gerard O'Neill that's basically a cut and fold O'Neill cylinder model here. So in order to describe the geometry of the space to Don, O'Neill sketched this and sent it to him, and Don photocopied it first and then cut out the photocopy to make a little paper model of the thing that he still has. So then also, of course, there's the influence of science fiction in this project generally. Gerard O'Neill kind of tended to disavow the dialogue between his own work and science fiction for understandable reasons, but the two artists were really involved in science fiction fan culture. They had read, of course, Ringworld and Rendezvous with Rama, and in Don's case, he had even illustrated the cover of Ringworld before embarking on the work for the 1975 study. And then in contemporary terms, of course, like technology companies have sort of adopted the language, the visual language of the paintings, but also the formal language of the 1975 space settlement studies. Here at Apple's campus, this is Norman Foster and Partners, which is, of course, complete now. And then this is under construction, the Google headquarters done by Bjarke Ingels Group and Thomas Heatherwick. And I think it's especially interesting to note that, not only does this sort of reenact some of the paintings, in this case Rick Goodis's Stanford Taurus interior, reenacts kind of note for note all the elements of the space and all the elements of the painting, but also this building is under construction right across the street from NASA Ames, where the original 1975 summer study took place. Thanks.
Thanks, Fred. Great pictures. It brings back reading those books back in college or high school or whenever it was I read them, and living through that time but not being a participant. So, Bob, I'm glad you got to participate in that. That had to be a wonderful experience. So, a quick question. What do you think we need to pay attention to the most as we build these larger facilities that we're going to start talking about?
Well, one of the stories that I came across while doing a close read of the original literature, especially the NASA report, also titled Space Settlements, that I think came out in '77, is that there didn't seem to be a lot of like different design groups talking to one another. For example, the urban planners had gone off in their conference room and they had done a lot of research on global cities and how much public space different global cities had. They wanted to make that answer, given that space is a premium, how much public space should you create?
Right.
And they found a number that they liked, and then they cut that number in half. Mm-hmm. And in the report, they cite the fact that, of course, these habitats will have agricultural areas and that those could double as public space. Meanwhile, over in the agricultural section of the report, the agricultural experts have decided that in order to maximize the production of food, they would make these spaces like sunlit for 24 hours a day, supercharged with carbon dioxide, 90% humidity, and 90 degrees Fahrenheit. So this is not a nice place to go and take a walk if you're getting stressed out living in an artificial environment. So, and I think it's not just a sort of snafu that can happen in, project management, say. I think it illustrates the idea that when you have all these different expertises at the table, they're all going to we all do this, we're all going to tend to try to optimize for our own discipline. And so coordination is really, really important, not just in the different systems of the habitats themselves, but in the different cultures that are coming together to design artificial cities in space.
Okay, great, thanks. Appreciate that. Our next speaker is Susie Bianco. She's going to talk to us about her master's study and a 400-person facility in space. And this is still a zero-G. Come on up, Susie. There you go. And arrows.
All right.
Yeah.
Thank you, Dallas. Hello, everyone. Good morning. It's nice to be here today and be able to talk to you about my project. So this is a very conceptual study that I made for my thesis project for my space architecture thesis. And it's not meant to be a study of feasibility, but more of just general considerations that we need to make in order to build larger space facilities in orbit. So my outpost is called New Venice, and it is a multi-industry outpost for about 400 people. And by multi-industry, I mean that whatever business you want to do in space, that would be the place to do it. So if you want to manufacture, if you want to do research, if you want to do tourism, whatever you want to do in space, that would be the place to do it. So in my research, I looked at existing, the stations that have been proposed, the stations that have been built, and I found 3 challenges to focus on in order to create my own. And you might recognize the silhouette of the ISS. And these little images, they just kind of illustrate the different types of activities that go on inside. And you might notice that there are a lot of activities that aren't compatible happening in the same places. And it's a very tight space. So there's always going to be some type of conflict. People sleep in the same place where they conduct research. They eat in the same place where people pass through. So it's not an ideal configuration. So the three challenges that I chose to tackle for building a larger space community would be to create a comfortable environment that would be both stimulating but psychologically comfortable for the humans that are in there. And breaking away from this, we have two concepts historically. One is to bring Earth to space and adapt Earth to a space environment, and the other is to put humans inside little machines and adapt them to living that way. So my idea is, how can we do something different and create a space that is tailored for humans, that is tailored for microgravity, that we can actually take advantage of what that brings. Second challenge is to cater to the diverse uses that I'm putting in this station. So if you have manufacturing happening at the same place where you have medical research, how do you integrate things in a way that one activity doesn't interfere with the others? And a third challenge was to simply break free from this traditional station building concept that we've been using of just attaching a little module next to each other and making this corridor station. So those are the three challenges. And my approach was to create a hybrid outpost that could combine both traditional station building techniques with new developing technologies and create something that would be a little bit more suitable for a larger population. And just keeping in mind that this was meant to be built in the next, not in the next, but 50 years from now. So I'm extrapolating technology a little bit. So my idea was to zone my outpost into different types of uses. As an architect and urban planner, I have this background in zoning, and I understand that certain activities need to take place in a certain distance from other activities, but at the same time, you can't completely isolate zones and not provide an integration. So what I did was I created clusters, and these clusters concentrate different types of activities that are similar in needs and requirements, but they're also integrated to the entire station so that it's not any isolated thing. So these cluster 1 is actually a little bit different than the rest of the station because it's actually isolated modules. Any hazardous activity would happen in these, and these would actually be flying, not flying, but they would be orbiting near the station. They wouldn't be actually attached to the station. But the people working in them would still be able to live in the community and take part in the community activities and enjoy all of the amenities that are offered. The second cluster would be the backbone of the outpost, and all of the maintenance and support activities that are needed and necessary to keep such a huge outpost going. So administration, maintenance, shipyard, spaceport, logistics, everything would be spread in this cluster. And would be that's where they would run the colony. So for this, I used mainly existing types of modules. You can see I have cylindrical modules and some inflatable ones. I have a different one that I will talk about later, but mainly using what is available, but extrapolating a little bit on size. Cluster 4 would be actually the main activities of these outposts. So the actual money makers, the actual modules that companies would lease and use in space. So if you're a startup, a space startup, and you want to create I don't know, space beer. You could lease one of the modules in there and use it to brew your own beer. So for this type of, for this, since there are many different uses and so many needs, and each activity, each function will have different needs, I created separate different types of modules. So you have the regular tin can, where you would lease maybe a small space, a small laboratory space, but you also have the big inflatable modules that you could lease, the whole thing or just a section of it. There are inflatable donut-shaped modules that you could use. So I try to cater to different needs, and the station would offer the infrastructure necessary for each need. One of my ideas is that to have these modules that are connected to the station, but at the same time they are a little bit separate. You don't have a permanent corridor connecting it to the station. So you have it isolated. You can do whatever you want in there, and it won't interfere at all with external activities. And you can access it through a type of elevator train kind of thing that would go around this ring and just give you access to the modules and to the station above. And then finally, cluster 3 would be the community cluster, where people would actually live and have their daily leisure time, and just that's where they would live. And that's also where the tourists would come to visit. You want to go to space, you want to actually experiment microgravity, you want to fly around, you want to see what it's like to be weightless. So I've created these 3 community islands, which, come back to that, which is just this big open space. It's not that big, it's 15 meters diameter, but it's much bigger than what we have today in any available module. And the way I designed it, I put individual habitats on the walls, little individual habitat pods, and then all the space in the middle is wide open with these spheres that would house restaurants and cafes and stores and just other things that people need to live. And it would just be this wide open space where people would jump around and enjoy being in microgravity. And of course, there would be a more organized transportation system throughout the station, where people would actually, hold on to rails and be taken towards wherever they want to go without the confusion. But I think it would be more fun to just jump around. And in order to build this large open space, I came up with this idea that I call pressure envelopes, and it is a bit of an extrapolation of current 3D printing capabilities. I looked at Tethers Unlimited and now I forgot the name of the other one, but and they're experimenting with 3D printing structures, and I thought, what if we could 3D print something a little bit more continuous, like a loop, and then as you print one loop, you go around and use that as a guide and print the other loop and just create this spiral. And then you could have another type of robot that would wrap everything around in airtight membranes and just create this large cocoon type of structure that you see here. That would allow you to have large space, large open spaces within, and just make a better use of the space that we have. And just to end, this is an inside concept of what it would look like to be inside of one of the community islands. So the little things you see on the side are the individual habitats, and all the space in the middle is where you would do have your fun. And the spheres would house all the amenities that you would need to just have fun. Thank you.
Thanks, Susie. Very, very innovative thinking on how to create a facility without actually knowing what's going to be in it, and how do we do it. So I think the spiral construction, a spring-like, building a coiled spring and then wrapping it around, very innovative approach to building large structures in space, which is really going to be a problem. How do we create that construction industry? So thank you. And speaking of construction, our next speaker is John Blincow, who will talk to us about Gateway and what they're planning to do in terms of the construction industry in space.
And this button right here to advance it, right? Arrows would probably be best. Right arrow then? Right or down? I'll figure it out. Yep. Thanks. Thank you, everyone, for coming here today. First off, let me say something important. There is nothing else more important than the effort to build spaceports, orbital farms, cities in space, factories in space. Humankind's first large-scale home off-world is going to be in orbit around Earth. Now, if I owned a rocket company, and I don't, but if I did, I would start seeking launch contracts for the biggest, most lucrative area of human expansion in space for the next 100 years, space construction. In May of 2012, I was looking at an old image of a spaceport, very similar to this one here. And I asked myself a question: how come we don't have this yet? What happened? It became pretty obvious that NASA is never going to build anything this big. They'll never get the budget for it. In October 2012, I quit my job flying 747s, and I started the Gateway Foundation in the effort to build the first rotating spaceport. Why? It's personal. I want to go. I think everyone here wants to go if they had the chance. If we form a space construction industry, some of these designs that you have seen today will be built, and many of the people in this room will get their chance to go. So how do you build a spaceport? Very quickly, we realized that the biggest problem was a lack of space construction assets to build it. So we made a video showing how it could be done. But what we really need is a space construction industry. So what do you need to start a space construction industry? You need 3 essential things. One of them is the first space construction company that could acquire the tools that are being made so that you can make things in space. We started working on orbital assembly 4 years ago. We knew nothing was going to get built without a SpaceCon tools and machines. In 2015, I came up here to meet Dr. Robert Hoyt, CEO of Tethers Unlimited. He was making 2 amazing space construction machines, SpiderFab and Trusselator. But I knew I had to meet more people. I met Phil Spampanato, who is the director of technology at ILC Dover. They make spacesuits. Then I went out and I met Nick Zello, who is the vice president of MDA. They make the Big Canada arm. And they also make an amazing space construction robot called Dexter. Now, NASA calls Dexter the hand of the arm, which sounds very Game of Thrones. But actually, it's an amazing space construction robot that can do a lot of things. It just lacks mobility. It has to have the arm to get it around. After getting these people together, we also got a bunch of JPL scientists and Caltech professors, some NASA people, a JAXA astronaut wanted to join our group, and we put forth a study proposal to the Keck Institute of Space Studies, how to build the first rotating spaceport. Sadly, they turned us down. They said our idea was too big. So we moved on. Next, we got to designing drones that we would need. This was a project we called EOR. Now, you might have got some of the pamphlets out the front there describing what it is. EOR stands for Errant Object Retrieval. These are 3 drones designed to go out and fetch the tools and parts that are floating away from astronauts and bring them back to the construction site. This is really important. Space construction has the potential to create a far bigger mess in space than we've ever seen before. With designs and prototypes for bots, pods, and drones, we decided to find a project to build so that we could get out there and test these tools and machines. So, our first SpaceCon project was Von Braun Station. This started out as the Von Braun Rotating Space Station X Prize. We were going to make a proposal to the X Prize Foundation to start a competition for the first rotating space station. We got all of our materials together. I was going to drive down to Studio City to talk to the guys who are running the show down there. And we decided, you know what, let's do this ourselves. So, we were looking at some other projects too for a while. We were looking at space telescopes. We had a project Copernicus. It was going to be a 30-meter primary mirror. But when we talked to Ball Aerospace, who makes the mirrors, they said it's a long process. You have to bake the mirrors for 2 years, you have to grind them for 2 years, you have to polish them, then you have to calibrate everything. We thought, you know, forget it. We like the idea of building this space station better because it's going to use almost all of our space construction tools that we want to have made. Now, in order to build this station, you would have to have some advanced space construction machines. And if you've seen our videos that show a machine that we call the G-Cell, it's building a spaceport rather quickly. It's using modular construction to fabricate huge areas of a space station in only days. To build this station, we would have to build a large truss that would support everything called the ORT. A derivative of the G-Cell is something we're going to start working on October 1st of this year. We're going to build a prototype. The VBTAL is what we call the new derivative, Von Braun Truss Assembly Line. This is the G-Cell, the previous rendition of what's going to be the Von Braun Truss Assembly Line. The Von Braun Truss Assembly Line can build things so quickly that when you look at this truss, the outer ring truss for the station, it can build the entire thing in 1 day. Now, I don't mean to brag, but we could build it even faster than that. But there are actually 2 cells in the manufacturing facility. There's one where you do the welding, and the second one where you have to do weld inspections, visual and radiological. But that's just half of the problem. To start a space construction industry, you need the tools and machines like we talked about. You need at least one space construction company to buy those tools and machines, take them up to space, and to test them out. But the big component that's missing, the thing that's going to start a space construction industry all at once, well, we all know what that is. That's money. You're not going to get anything built without money. And in this case, we're talking about a lot of money. Funds for the tools, funds for the space construction company that's going to do it, and then the funds for the station that you want to build. So, we're announcing the formation of a fund just for space construction. It's going to be called Orbital Equity. This fund is going to dedicate funds towards people who want to make tools and machines just for space construction. Now, who will invest? Many investors, because the returns are enormous. But we are looking for one investor in particular to show leadership here, the most successful businessman in history. He wants to build large structures in space too. This is his town. So I say we should invite Jeff Bezos down here to talk with us. If he wants to come down here, there's lots of smart people here, lots of good ideas. And he's going to need these space construction tools and machines because he wants to move factories into space. Now, before I end up here, I'm going to talk about some new features of Von Braun Station. You guys probably picked up a couple pamphlets at the front. But we're thinking about a couple of things that could be interesting. One of them is an ice shield. We're going to have residual water from the station. We could form the water into plates to give increased radiation protection for the people on board. This is just something new that we're throwing out there. We haven't finished it. It's kind of a study we're working on. The second one is a magnetospheric shield, an EM shield. Our station here, the Von Braun Station, produces an enormous amount of power, 4 megawatts. We could up that even higher. There's lots more room to put more solar power panels onto it. NASA has a program called MDT, Magnetospheric Dipolar Torus. This would work really well with the station if we had enough power to do it. And that's about it. If you guys have any questions for me, feel free to ask them. And by the way, thank you, Dallas, for inviting us, and thank you, Ed.
Thanks, John. I think you failed to mention the size of Von Braun, which is also 400 people. Is it, the Von Braun station is 400 people, correct? Yeah. And then the gateway is?
1,400.
1,400.
1,400.
Thank you. And Susie, also your station was in L5, correct? And John, yours are in low Earth orbit.
Yeah, sun synchronous orbit.
Sun synchronous orbit.
Yes, so we're there because we want the power and we want the thermal
Right.
stability.
But you're not on the path, not on the direct pathway to any place beyond Earth, like the moon or anything like
No,
that.
no,
So
it'll stay in low Earth orbit.
strictly an Earth-centric facility.
Yes.
Okay, great. So moving on, I believe, to even bigger facilities, but still in low Earth orbit, is Al Globus and his concepts for habitats that are closer to Earth and easier to build.
Thanks. I want to talk about space settlement, and for the purpose of this talk, I want to define space settlement as a place where you raise your kids. No kids, no space settlement. Something else. It's a hotel, it's a workplace, or whatever. Okay? Now, we're all familiar, or the vast majority of people here are very familiar with the old O'Neill studies that come out with settlements. It's a beautiful and wonderful vision. And it hasn't been built. So why not? And we can say, well, we don't have enough money. So we can turn that around. You say, I don't have enough resources, we can't do it because it's too big and nobody will come up with the money and so forth. Well, there's a couple ways to handle that. One is to complain about it, and the other is to make the task easier. Mathematicians do this all the time. They convert a problem from one domain to another in order to make it easier. Okay? So what is it that we have to deal with O'Neill settlements? Well, the first thing is they're too bloody big. Okay, Stanford Torus is almost 2 kilometers across. It's more than a mile across. You know, when we started building bridges, we did not start with the Golden Gate Bridge. Right? We started with little teeny things over creeks, and we worked up our way up. It's too big. Kilometer scale, you don't start there. It's too massive. It's located at L4 or L5 or other high Earth orbit, and that means that you aren't really protected much by Earth's magnetic field from cosmic radiation. And so the mass of systems is typically measured in millions of tons. Now, using our mass model, which is a little different than the one used in the 1970s, the Stanford Torus is 13 million tons. That's an immensely difficult thing to work with, that much stuff. We need to get rid of most of it. It's too far away. Okay, it's pushing 400,000 kilometers away. That is a long supply line. And talk to anybody who manages supply lines and they will turn green at the idea of trying to deal with a 400 kilometers supply line. There's too much essential R&D. You have to figure out how to mine the moon or asteroids. You have to figure out how to package the materials. You have to figure out how to transport the materials. And you have to figure out how to use them when you get there. Now, it's not that any of these things can't be done, but every one of them makes it harder to do the tasks at hand. And the other thing is there doesn't seem to be any incremental path. Can you do a little bit of work and get some value? The Silicon Valley is in love with this concept of the minimum viable product. What's the minimum viable space station? And that's what I'm going to try to define and see how to get there. In any case, the net result of all these is there aren't any settlements. Okay, we all know that. Let's see here. So, there are 4 keys to breaking this conundrum and bringing the cost and the size and the distance and the mass of the first settlement down to something that we might be able to pull off. Okay? And what I'm talking about is in this chart on your left, the center column, column 2. So the ISS, you can see the mass, the size, population, how far it is up. How many SpaceX Super Heavy launches would be required to launch it if they're mass limited? And so there's the ISS. We know we can do that. We did it. Okay? The second one is Cooperative 2, which is if you apply these four rules, actually the first two of them. And the third one is the Stanford torus. You can see that the Stanford torus is multiple orders of magnitude bigger, farther away, more massive, and so forth and so on. And that's why it hasn't been built. Okay? So why can we get away with Cooperative 2? What is it that makes it, what's the secret sauce? Well, the first part of the secret sauce is don't put it at L4 or L5 where you get full radiation exposure to deep space. Put it in low Earth orbit and keep it directly over the equator, equatorial low Earth orbit, because that's a region of space where radiation levels are very low. By space standards. They're not low by terrestrial standards, although they are less than some terrestrial environments. So you put it close, maybe 500 or 600 kilometers, a circular orbit, and you must have very, very low inclination. And if you do that, you may not need any radiation shielding, and you certainly won't need very much. And I will go through a set of slides that will hopefully can show you the data behind that and why that rather surprising claim might be true. So that's the first thing. It reduces the mass of the system by a factor of around 100. Okay? It's talking about big changes. The second thing is spin fast. Okay, the Stanford torus rotates at 1 RPM. And if you don't want to rotate any faster than 1 RPM, and you want 1 G, because remember, we're going to have children. And children would, I think, at sort of a minimum, you'd like them to grow up with bones and muscles. I think that's a good idea. And so you need some gravitational stress, because bone and muscle develop in response to stress. If you raise people in micro G, they're going to be extremely weak. If you raise them in 1/3 G or 1/6 G, we don't know everything is going to happen, but it's a pretty fair bet you're not going to visit the Earth very often. I just reread The Moon is a Heart's Mistress, and they have a whole section on that. If you spin at 4 RPM, you get 1 G with 112 meter diameter. Okay? And the reason that people say, no, we don't want to do this, is if you spin people at 3 or 4 RPM, they'll get sick. That's true, they will get sick. But if you read the whole paper, you'll discover that they also get better. If you put a group of people in a rotating room and you spin them up at 4 RPM, all of them will get sick, except people will have damaged otolith function. And most of them will be better within a few hours. A vast majority of them will be fine within a couple of days. There is possibly a small minority of people who will never adapt, in which case you're going to have to refund them their money and send them back home. Okay? Now, that doesn't say that we should have a 100-meter settlement. It means that rotation rate is not what determines how small a system you can build. That's determined by other factors, social factors. I mean, how many of us really want to live in something 100 meters across? Now, I'm not talking about visit, not go and play around for a week, or not go and work on the interstation, but live and raise your children on something that's 100 meters across. Probably not a whole lot of folks, okay? So this is just a minimum bound. You're probably going to be looking at something larger, but if you accept that as if you're going to do it, and you can see some of the, I don't know if you can see in the bottom of the side over here, you can see some of the consequence of that. There's a very high rate of curvature in your living environment. But in any case, if you apply these two, you get those numbers in the Cooperative 2 column on your right. And notice that the masses and the sizes and so forth are not that different from the International Space Station. They're about a factor of 20 or so in mass, a factor of 1 in size. Population is, it's a fairly large factor, just a factor of 80 or something like that. You need 60 SpaceX super heavy launches, if mass limited, which is a lot. But we can launch something 60 times. We can do that. Okay? We can't launch something 90,000 times. Okay, which is what you have to do in order to do the Stanford torus. So what this says is if you apply these first two, that with a really good vehicle, you might be able to get away with building your settlement in low Earth orbit and just launching everything from space. You don't need extraterrestrial materials. You can use them if you can get them, but you don't have to have them. Okay? So if you go to key 3, reusable low-cost launchers, that's being done. That's being done here in Seattle, and it's being done in the various places where SpaceX works. And if you look at if you take the most optimistic rumors going around the valley about the performance of the SpaceX Super Heavy and the Starship, then it almost, or maybe even just barely, meets the requirements to keep your system, to be able to launch a space settlement from Earth without extraterrestrial materials and keep it supplied as an initial step. This isn't something we stay in forever. And the last key is tourism. And the reason that it is because a space hotel has requirements fairly similar to a space settlement. So you can build a small hotel, which you can do in a single launch, and you can start getting revenue. Remember I talked about incremental income? And if your small hotel is successful, then you build a bigger one. And you build a bigger one than that, and you build it. Eventually you get one the size of Cooperative 2. Something that's on the order of 112 meters across. So you build a couple of them to get good at it, and then you re-engineer for the stronger structure you need because you're going to be rotating and so forth and so on, and you build your first space settlement. And I believe this is the easiest path to true space settlement. I could be wrong, but I think it's fairly good. Okay, and you don't need lunar mining, you don't need in-space transportation. You can have them. So the most startling claim here is that you either need very little radiation shielding or no radiation shielding for the first space settlement. And here I'm going to tell you why. This is a cartoon of the Earth's magnetic field. And it has a pointer to the location by symmetry of Cooperative 2. Okay, so the radiation that is a primary concern is cosmic rays. It's not the only concern, but it's the only one I'm going to go into here. Cosmic rays are omnidirectional. They come from every possible direction. They come in many different energies, and they come in many different sizes. Okay? Now, any particles coming from your right will be absorbed by the Earth. And you get a factor of 2 in reduced radiation right there. Low and medium energy particles coming from your left will be diverted by the magnetic field lines and produce aurora borealis, pretty pictures for the Eskimos. The only particles that you will be subjected to in equatorial low Earth orbit is very high energy, relativistic speeds, massive iron nuclei, cesium nuclei, stuff like that, particles. These are very damaging particles, but there aren't very many of them. How many? Well, here's some measurements. This is a little higher than we're talking about. We're looking at 500 to 600 kilometers, which has a little more radiation. This is at 400 kilometers, but we have data from the International Space Station. Every dot, every colored dot there tells you that's a measurement of radiation. The blue dots are low energy. You can see the scale on the right-hand side. And the red dots are high energy. It's a log scale, so it's a factor of around 500 to 1,000 difference between blue and red. And you will notice that everything's blue except for over South America and the South Atlantic. It's called the South Atlantic anomaly. And most of the dose that the ISS astronauts get are received in that location. The rest doesn't really contribute. And for example, they plan, I've been told anyways, they plan EVAs so you don't pass through it just because of the high radiation. So the question here, okay, now in some sense we know how much radiation you're going to get. Is that more than you can accept? What's acceptable? How much radiation is acceptable? I spent a long time reading very, very boring books about this, and eventually came to the conclusion that a reasonable limit, maybe not the best limit in the world, but a reasonable limit, is the occupational dose allowed for radiation workers. X-ray technicians, nuclear power plant operators, and so forth, that would be a reasonable limit. That limit is 20 millisieverts per year. A sievert is a measure of the biological effect of radiation. Okay? So if we could show that in these orbits, radiation was less than 20 millisieverts per year, and we can say how much radiation shielding we need to do that, then we could say something about whether we can do what we claim, which is we might be able to build these things with either no or very little radiation shielding. And that has a massive effect on the mass of your system. It's radiation shielding is 99% of typical designs. So these charts are calculations done with Alteris. I did these. Alteris is NASA's front end to some airfare radiation codes that allow you to say things as, given this orbit, and given this time, because radiation varies quite a bit, and given this amount of shielding, how much radiation will be experienced by an astronaut or a biological sample in this particular case. So the numbers on your left are for deep space, okay? The leftmost column is the tons of radiation shielding per square meter. The columns are for polyethylene shielding, water shielding, and lunar regolith shielding, okay? Now, I just want, in case you don't remember, the 1970s thought that they could get away with about 5 tons of lunar regolith per square meter. Now, if you look at the numbers in the interior of the charts, for instance, two tons of polyethylene shielding in a year, or the year that this study was done, you get 137 millisieverts in that year. And this year was specifically chosen because it was a bad year. There's more radiation than you usually accept. But if you look down at 7 tons, you can see if you have 7 tons of shielding polyethylene or water, that is sufficient to get your population below 20 millisieverts per year. But if you want to do that with lunar regolith, you need 11 tons, I hope you can see that, of regolith. So that's the situation in deep space. That's why you need, millions of tons of lunar regolith in order to be able to live in L5 or L4. But if you go to equatorial low Earth orbit, the story is different. Again, the column on the left is tons of radiation shielding, but it goes to 750 kilograms. It doesn't go to 11 tons. This is polyethylene shielding. The second column is if you have a 500 kilometer orbit, circular orbit, and the third column is 600 kilometer orbit. Now, if you look at zero shielding, which actually isn't quite zero shielding because Alteris can't handle zero shielding, it divides by 0. So you had to give it tiny, tiny, tiny little bit of radiation shielding to make it do the calculations. If you look at the zero, you get 17.7 millisieverts per year for that particularly bad year, which was back in the 70s, by the way, at 500 kilometers. Well, that meets our limit. And that's why we claim that you may be able to build space settlements in low Earth orbit with no radiation shielding at all. Now, of course, you will actually get radiation shielding. You're going to have the hull, you're going to have the life support systems, you're going to have bodies of water, you got all kinds of stuff that's going to give you a certain amount of shielding. But we're not going to even consider that now. However, at 500 kilometers, you come down fairly quickly. At 600 kilometers, you stay up quite a bit longer. In that case, you would need 100 kilograms of radiation shielding per square meter if all the assumptions are more or less right. Okay, so this is the key to making equatorial low Earth orbit a great place to start, not end, to start space settlement. There we go. Okay, so what's the financial story? Right now, space settlement is living off of angels, namely Elon Musk and Jeff Bezos, and they're doing a great job, but we cannot expect this to continue forever. I think the right economic model is a real estate model. You build a subdivision in space, and you parcel it out, and you build condominiums on it, and you sell those condominiums. The condominiums come with an ownership of a share of the hull, the space farm, the communication systems, and all the other sort of stuff. Now, if you take the most optimistic rumors floating around about Starship and so forth and so on, and you assume that the cost of the stuff and construction is no greater than the cost of transportation, which is a big if, by the way, then you can argue that this costs a couple about $5 million to move in. Now, this is a real estate business, so what you do when you need $5 million and you don't have $5 million, you take out a mortgage. Okay? You have $1 million mortgage, you're going to have to be pretty well off, and you've got $4 million to pay off, $4 million mortgage to pay off. I'm sorry, $1 million down. Okay? So the problem of financing a system like this boils down to paying off that $4 million mortgage. And the first step to doing that is you just keep your job, the one that made you the $1 million in the first place. Okay? Because this isn't going to happen for decades. No way. Okay? And in that, if you think, say 20, 30 years, okay? Now think back to the Earth's communication system 20, 30 years ago, and look at the unbelievable, this can do anything. It's just unbelievable what's happened, and there is no reason to expect that it won't be that much better in 20 or 30 years. So the first step is keep your job, the one that made you that first $1 million, and work remotely. Okay? The second step, which starts to take advantage of that location, is to build very large satellites that won't fit in a fairing. Now, that can apply to very large communication satellites, but it really comes into its own if we can somehow make space solar power work. Okay? Space solar power means gathering energy in space, beaming it to Earth. Enormous market, about $1 trillion. Now, if you wanted to build space solar power systems, you would not build Kalpana 2 first. That would be a diversion from your task. But if Kalpana 2 is already there, and you have 500 people who really understand space and who have terrific testing facilities, you would be a real fool not to seriously consider hiring them for the task. Okay, and then the government has a role. We'll bore you with that. These ideas can be found in a book. This is a book that's available on Amazon. The title we ran by Gerard O'Neill's widow, and she gave it her blessing. Didn't have to do that, but it seemed like the right thing to do. And if she had denied it, we wouldn't have used this title. There are also 3 technical papers on my website. If you search for Al Globus Space Settlement, you will find it without any trouble. And these papers are about 40 or 50 pages long. One is on radiation, one is on rotation, and the other is the implications of those 2 for system design. Thank you very much.
Thank you, Al. So the real problem is radiation and mass. Yeah. And maybe rotation speed, but not really.
I'm sorry, what?
Rotation rate, maybe. Because we can get around that.
Yeah, but I mean, if you're, you could do it with a dumbbell or a torus or something
Right.
like that. But basically, you still have to build this very big thing. You know,
Right.
you have to build something 2 kilometers across at 1 RPM.
Yeah.
Any way you look at it, that's hard to do.
Yeah.
Much easier to build a 100-meter thing.
Great. So we have one more talk, and that would be Anthony Longman, Skyframe Research, and he's going to talk about how we can integrally or dynamically grow a space station or habitat while we're living in it. And we have to change machines, so bear with us. Unplug this one.
That's great. Oh, thanks.
All right. All right. First of all, I want to tell you how I got into this.
Stand
11
closer
years
to the
ago.
mic. Stand closer to the mic.
First of all, I want to tell you how I got into this. About 11 years ago, my wife and I were living in the mountains north of LA at about 6,500 feet, up the side of a valley with an amazing view across the valley floor filled with trees and meadows. And I remember thinking there's got to be a way to make more places like this, and I mean in space. I've worked most of my life as a designer of living space for families with a side interest in landscape. But I've also done computer-based visual effects work in Hollywood. So the problem appealed to me. For several years, these ideas fermented, and then in late 2012, I met Professor Robert Skelton, who was then a professor emeritus in mechanical and aerospace engineering at UC San Diego, with a string of credits that included the Hubble and Skylab missions. What had grabbed my attention was he had figured out and published 3 years earlier the math for how to engineer tensegrity structures, something no one had been able to do up until that time. And I hoped that he might be interested in helping me build landscapes inside space habitats. So landscape is a big thing for me. And I agree with Al that space settlement is barely about raising kids. And that's why landscapes for me is so important. Buckminster Fuller once described tensegrity as islands of compression in a sea of tension, and it underlies a system of bones and muscles and tendons that let us walk around and hold things in our hands. Tensegrity structures are widespread in nature, and the reason for this is because of the inherent efficiency in the use of materials and because of tensegrity's flexibility and ability to change shape. In fact, Bob wrote the math that proved that tensegrity solutions are the most mass-efficient way to solve the 5 classical problems of mechanics. So this makes it extremely useful as a tool in space where every pound of material is precious and deployability is extremely valuable. I came away from that meeting realizing that the whole habitat
should in fact be a tensegrity structure, and that it might be possible for a rotating tensegrity habitat to undergo repeated structural expansion. That summer, we applied for and won a Phase 1 NIAC grant to pursue this idea, followed 3 years later by a 2-year Phase 2 follow-on grant to continue developing the concept. And in a moment, I'm going to share with you the fruits of that study. The full report will be available online later this fall and documents what amounts to close to 3 years of study and development, because we kept going after the money ran out. The core idea and the reason we were funded is to discover how to make a rotating habitat with geometry that supports a repetitive growth process. Then it can start very small and grow to a much larger scale that can provide 1,3G through rotation at whatever rate of rotation you decide is comfortable, whether it's 2 RPM, 4 RPM, whatever. With shielding, at least at 2 RPM, that means that the whole structure is about 1/3 of a mile across. This matters because for habitats to be truly livable, habitable spaces, and I don't think we should be planning to make anything less than that, we need to find a way to make them less expensive to build. So what this means is we need to find an evolutionary approach to building so we can make them affordable, that we can actually build them. Another key member of our team was Joel Sassell. Some of you may know. Joel's company, Transastra, plans to mine asteroids and lunar polar ice to make and sell rocket propellant. Transastra provided cost comparisons that grounded our study in the real world. By far, the greatest mass component of our habitat, around 99%, is in shielding and soil, which must come from asteroid or lunar mining. This will make the lifetime cost of building the habitat at least 20 times cheaper than if these materials had to be lifted from Earth. Now, to give you a little flavor of what that means, I'm going to start the slides with a part of an animation that I made for Joel, showing a Queen Bee robotic mining vessel deploying after launch and capturing a 30-meter diameter asteroid. Crash. Okay. Here we go. No sound.
Oh, you need to plug that. There's a sound cord. Sorry. Here's your...
We think that a lot is riding on the success of both lunar and asteroid mining. And asteroid mining in particular holds out great promise for the habitat enterprise if the risks can be reduced enough through appropriate technology development. This represents what I think is probably the most promising current approach to mining asteroids. And it's the animation has been slightly abridged to fit within our time constraints. If If you find the right asteroids, and of course that's a big deal, then up to 10% or so of the mass can be water, which can be processed into rocket fuel, rocket propellant. And we plan to use the slag from the processing to make the shielding in the shield floor of our habitat design, as you will see in a few moments. What I'm going to show you now is the result of 3 years of study of how to make a rotating space habitat that starts very small, but is readily expandable using a repeated growth format, allowing it to grow as large as desired, typically to 224 meters at 2 RPM. I want to make clear to you that you will be seeing 2 slightly different versions of this idea. The version with the trees and landscape surfaces was completed around April of last year. Is this running yet? Okay. And was a statement of design intent. The second version was completed this summer and was what you're seeing here. So that's the landscape version. And what we're going to see now is an analysis of what underlies the design. These are the objectives that we want to get to. And you can see that there's an extraordinary expansion of size that's accomplished over a series of 16 primary steps. We're going to see the beginning size in a moment. First of all, there are 3 basic parts. There's an outside shield, and then a bearing, 2 bearings, and an inside pressure hull. And in the middle, you have a 0G reflector that includes 0G industrial space. There's the pressure hull. Potential candidates are UHMW and graphene. And the solar reflector in the center with the 0G industrial space inside. For that to work, you have to have 2 bearing sets that allow these to be separate rotationally. You can see the kind of expansion that we're getting involved with here. And an overall expansion of about 18,000 times. The whole design of the habitat is driven by the need to make maximum use of sunlight and to share it between different applications. In practice, this requires rotation in the ecliptic plane and dividing access to sunlight for the crops and living space on a timeshare basis, like Earth's day and night channels, day and night sides. This also requires that they have opposite seasonal cycles. And we have to provide channels for the light to reach the interior, as you can see here. There we go. And to do that, we need a switching mechanism, which we'll get to in a little bit later. Now, new floors have to be added at the rim. And in order to do that, we have to provide a doorway at the bottom, the doorway through the shield. So that the shield has to let materials in all the way around the edge and yet still protect the interior. Of course, the shield must grow before the pressure hull can grow. And it turns out what we need to do is to prioritize radial growth first and then grow, once you get out to 1G, then grow sideways to maximize on that. Because the shield is massive, it needs to only rotate slowly, if at all. And so we need to have these bearings. And because the shield must move out, you have to have basically a translational capability in the bearing. So now we're going to see the deployment sequence. And this is going to move quite fast. As things appear, I'm going to try and introduce them. One of the things that you will see in a moment is that we will add some shielding around the outside. That shielding will probably be pre-positioned so that when the habitat is launched, they can be put together right away. The trusses that you see and the stowed pressure walls are for future expansion. And now you see the first solar panels and the first expansion as the inside, the central cylinder is cut and restraining cables gradually let it move apart. You're seeing now the loading decks either side being added, and also the translational bearings in red. The loading decks are in yellow. The blue, the ice green is a cooling system, set of cooling panels, which take heat from the interior out to the radiators on the outside. And in the center, you can see that there are a pair of sets of robotic arms which hold the edges of the floor panels and that load things, load materials, construction materials onto the floor, so you can build a new pressure hull floor you see there, raised into position. And the Mitchell trusses reach down from the pressure hull and grasp it as the robot arms let go, and then you seal and pressurize, and now you're going to expand sideways, and you have your second lateral expansion. And this is something you're going to see about 16 times, this kind of lateral movement. We now see the bioregenerative system installed, life support system, and the installation of the bearings in the center for the central radiator, reflector, which contains the zero-G space in the middle. We also have an interior pressure membrane because with a large volume that we're going to get to, finding all that nitrogen is going to be difficult. Now we see that the primary mirrors have been installed and are operating, and you're beginning to be able to see how the thing is going to grow. We'll see this sort of repetition of this growth cycle probably 10 or 12 times before we get out to full radius. You see what you're seeing now is a repetition of the exact same process happening over and over and over. This gives me time to catch my breath. In a moment, we're going to be out at 1G radius. And now we're going to adapt that method that you're seeing to grow sideways. Basically, instead of just adding one layer, we're going to add two layers, but at either side instead of on the outside. And that's going to allow the habitat to increase in width sideways. Again, the restraining cables are important here. And you can do this lateral expansion about 4 times before you run into the limit for tumbling purposes. You don't want to go any longer without active stabilization. And one thing to note here is that we can install a system of about 6 elevators on either side that can run up the inside of the glass shield and can reach all the way to the top, except for the last couple of floors near the center will have to be walk-ups. And at this point, we hope to be able to actually have access to cheap enough nitrogen that we can have an atmosphere that fills the center as well. So what we've been seeing so far, and one more thing, is once we stop growing outwards, we can then use the floor zones to transfer heat outwards. We can have a big dorsal radiator, whereas up until that point, we've had to settle with radiators on the sides. Now we're going to just look quickly at how the day and night cycles work. Basically, the crops and the interior on opposite sides of the diurnal divide. And that switch is accomplished by shutters on the face of the agricultural zones, plus some mirrors at the bottom. But the shutters do most of the work. And the question is, how do we do that? How do we reflect the light up the channel? I'm about to show you that in more detail. See, the bottom section is handled by essentially level-law type mirrors, louver type mirrors. But the rest of the deflection of the light has to be handled differently. And we're going to take a detailed look at that now. So how does this happen? We have a close-up to show this. what you can see here is that the face of the shutters are covered with basically linear prisms, and this is like the pentaprism on the top of a camera that reflects light internally, and so it's able to angle it up the shafts to the interior. I want to just outline, I mentioned we had two versions of the project. This is the landscape version, which came first, and then what you've been seeing in diagram form is the full growth arc. We know how to do this part, we just haven't done the calculations yet for this. But this shows, basically this is the goal, this is why you do this, so you can make a little piece of what we love here and take it with us into space. And we think this could perhaps be in an orbit between the Earth and the Moon, a lunar resonant orbit perhaps. A lot depends on how we can control, in terms of propulsion, and that's another story. But this is just a couple of more images before we say goodbye. And you can see that could be a pleasing place to be. About 10,000 trees, and approximately 8,000 people we think we can support. Oh, and Bob Skelton, yeah. Okay, thank you guys.
Well, thank you, Anthony. So the audience has been very nice and set for, 2 hours now? And listened to stories from Space Hab to 8,000, 10,000 people facilities, but maybe it's time for a little stretch and walk around and bio break, and then come back in about, let's say by 11:15, and then we'll get into audience questions and participation. And if you don't have questions, I have some planned. So see you back in 10 minutes.